Hello, and welcome to my video where I'll be solving a ideal gas chemistry problem. Um, I guess in a different kind of way. Um, so here's our problem here. An open container, initially at 1 atmosphere and 298 Kelvin, contains 1 kilogram of liquid water. The container is sealed without removing the air, then heated to a pressure of 2 bar, at which the point of vapor space contained 0.3 moles of water. What is the final temperature? What is the total volume of the container? And I'll be explaining my solution in a bit here on a whiteboard. And after that, I'll bring you guys back and we'll do it in Python Collaboratory.
Hello, and welcome to the whiteboard section. First off, as I move around here, it's gonna get a little noisy. Can't do anything about that old floor. So, if anything, you could probably see me fall through as well. So, anyway, let's start with approaching this problem here. Let's see what we should do. So, simple enough. First step, let's list our knowns and unknowns and finals, right? So, what do we know? Well, we know that the total initial pressure is 1 atmosphere, right? And well, let's convert that to pascals. So we get 101,325 pascals. And what else do we know here? We know the initial temperature, which was 298 Kelvin. And what else here? We know the mass, the total mass of the water here. Total mass of the water, that's 1 kilogram. And what are we looking for? Well, we're looking for the total volume and the final temperature. And what are our final parameters here? Final outputs. Well, in the final state, we know that the total pressure final was 2 bar, which is 200,000 pascals. And we also know that the amount of moles of the water in the vapor phase, so moles of water in the vapor phase, was 0.3 moles. All right, so before we get into the dirty stuff, we gotta look at this problem a little differently. All right, and this is what I mentioned at the beginning. So let's start off with changing the idea of what we think these unknowns are. So let's assume, just for now, that the only way that we can solve this is to plug and chug, all right? And we would plug in a random number and see if it gets close to that. And if depending on that, well, we change it up or down, right? And well, how are we gonna get from there, well, from here to there? And well, it has to be taking some sort of path, right? From this to our desired state, final parameters, right? And right now, our problem is that we don't know what these paths are, right? So that's what we're gonna do. What are the paths, are these variables taking with each other to be able to get to these final desired parameters, right? So let's start with that. Now, you might be wondering what these quote-unquote paths are, right? Well, these paths are simply the relationships that these variables have with each other. So let's start determining some of the relationships that they have. And simple enough, well, these totals have to be made up of some parts, right? So let me move these away for now. And let's just start with what we have so far on the initial side, starting with the total pressure initially. Well, we know that the total pressure initially has to be made up of some partial pressures, right? And what is there initially? Well, the container's open. So we have the air in there, and then the liquid, the water. It's just the air and water. So we have the partial pressure of the air initially, plus the partial pressure of the water initially. And through here, we have another unknown. We have some unknowns that we need to somehow connect. Well, what's another relationship with it? Well, like I said earlier, it's an ideal gas problem, right? So all of these gases are ideal. And with that, since this partial pressure water is ideal, in an ideal situation, we are able to, its nature resembles the curve on a phase diagram. And with that, well, what is that equation for the curve? Well, it's Antoine's equation, right? So we can solve for it, and well, partial pressure of the water initially is equal to 10 to the A minus B over C plus the temperature initial. And from there, we have finished this path for this, right? Now, how do we solve for this? Well, it's just a rearrangement of this, right? So we have also finished this path. So all in all, we are done with this. Moving on, temperature initial. What we can do with that? Well, it's sort of weird. It's its own path, I guess you could say, right? It's not dependent on anything. Things just depend on it. So it's sort of its own thing. So we don't have to really do anything with it. All right, so moving on. We have mass of the total water. Well, like I said earlier, it's gotta have pieces, right? So what does it consist of? Well, the mass of the water total consists of the mass of the water in its vapor phase, and it also consists of the mass of its mass of the water in its liquid phase. Simple enough, right? And well, once again, we have some unknowns again that we have to sort of find the path for. And well, start off this. Actually, let's start with this. Just because we have a step. Well, if you look here at what we have, well, we have two waters in the vapor phase here, right? Mass and moles. And well, how is mass and moles connected? Well, there's that path of molecular weight. And well, that's how they're connected. So we've established a path for that. So we know that the mass of the water in the vapor phase is equal to the moles of water in the vapor phase times its molecular weight, which is 18 times 10 to the negative 3 kilograms per mole. Alright, so we've established that path and finished it. And well, the one that I skipped earlier, the mass of the water in liquid phase, well, now we can solve for it, right? It's simply just its rearrangement. Simply just the rearrangement. And there we are, done with that path. Moving on to the ones I moved earlier. All right, well, we have the volume, total volume. That's got to be made up of some pieces, right? Obviously. So we have the volume of the vapor phase initially, plus the volume of the liquid phase initially. And well, that same total volume will also apply for the volume of the vapor in the final, and plus the volume of the liquid in the final. And now we have this. We have created 4 more unknowns, and well, with that, we have to find 4 more paths that will connect them, right? All right. Well, let's see here. Well, let's start off with some of the initials here. We know that the volume of the liquid initially, all of the water was liquid, right? And well, what are some things that we can use here to connect? Well, we have mass and volume. Mass and volume. That's density, right? Well, we've established a path here. So let's actually write it out. So we know that the volume of the liquid phase initially, well, all the mass of the water was, well, liquid. So we can use the total mass here. That's over the density of water. And then we can solve for the vapor phase initially with just some rearrangement. Right? And then now we can try solving for the final liquid phase, right? Because we know it'll end up being where we have to rearrange to find the volume of the vapor phase final. Anyway, same thing with the initial. So let's find the volume, the liquid phase, and the final. Well, we know now that there's some vapor, right? So it ends up being a rearrangement of this one that we found earlier to get the mass of the water to the liquid phase, which is mass of the water total minus the mass the water in the vapor phase all over, again, the density of water. And then, well, we've sort of finished all the paths connecting those, right? And next up, well, we have temperature final, right? And it's the same business as the initial temperature. It's sort of independent, obviously, and well, it's sort of its own path. It helps others, right? So, moving on. Right now, we have our initials all connected to each other with our unknowns / inputs, and now we haven't established any paths leading to the finals, our desired parameters. So that's what I'll be doing here now. All right, so let's finally make a path to our desired final parameters here. So let's take the same approach that we have earlier. So starting with the final total pressure. Final total pressure, well, that equals the partial pressure of the air final plus the partial pressure of the water final. And well, we know we know how to solve this already. It's the same exact method as this, but instead we use TF. Right, so how do we solve for the partial pressure of air final, right? Well, you could say that, well, we could do some rearrangement, but that wouldn't quite work, right? Because, well, we're trying to find the TF, so that wouldn't work because we don't have TF. So how would we find this? Well, ideal gas, right? So we have that, right? And well, we need moles of air, and I might have wrote this in a bad spot. I might not have it from here. R times temperature final, and that's all over volume of the vapor phase final. And well, we have another unknown here. And it's this right here, moles of air. And I'm just gonna create right there. Well, it's also, if we can't find it using the final parameters, we can try finding it with the initial parameters, right? We actually have a bunch of knowns for that. So let's do that. So we have moles of air. That equals, well, partial pressure of the air initially times the volume of the vapor phase initially all over our TI. And well, we've completed the path, right? We have established a path with all those already. And well, that connects for this, into that, and well, there we go. Right, we have now finished the path for this final parameter. It is now connected. And well, we can't leave out this, right? We still need to connect that somehow. And using the same principle as we did here, that's how we'll establish our relationship. Or relationship slash path. Right. So moles of water in the vapor phase equals, well, the partial pressure of the water final times the volume of the vapor phase final, and that's all over R times TF. And just like that, we have connected, we have discovered all the paths, all the relationships that these variables have with each other to find out how putting in our unknowns, V total, and TF will make it to our desired outcome. And with this, we're able to develop a code that will be able to sort of go through all the different type of values to find the correct value that will lead us to the right, down the right, using these relationships straight to our desired outcomes. So let's do that. Moving on to the Python code.
All right, welcome back, and this is going to be the Python section here. And so let's get to coding the solution here. So we'll be doing this in collaboratory again, and let's connect to a computer. All right, so we're actually going to need something special, and it's going to be another code. And to import this code, we will actually need to do a special command, something different from the usual. So it's going to be called Git Clone. So we'll be cloning this code over into this computer's hard drive. All right. And what code might it be? Well, it holds some tools for chemistry, and it will actually have the properties for water that we need later on. So here it is, CG tools, and we'll copy it right here. And we'll paste that in and shift enter. As of right now, it's cloned, but there's actually no pathway for Python to actually go and grab it. So we need to actually establish a path. So we'll import sys, and using sys, we'll do path.insert, and we want it to be on top. And where is it? Well, if we open up content, it's right here in content. So it will be /content/CHE tools. And it is successfully in. So now we can import. So now we can import tools.che as CHE, and we can also from scipy.optimize, we can import their root function because that's how we'll be finding the solution. Root will sift through all the possible numbers and land on the specific number to get our desired final, right? So we need the properties of water, like I said earlier. So we'll assign it to variable w for water, I guess, and w equals che dot the class props here, and we're gonna pull the object water. And just to make sure it works, and yeah, it does. All right. And now we can simply call w and pull whatever property you want of water. And I've taken the liberty to screenshot the whiteboard from earlier and post it here so that we can so it's easier for me to copy the data over here. So let's put some of our knowns in. So we know the total pressure is equal to 325 pascals. We know that the total pressure final is equal to 2e to the 5. That's also in pascals. We know that the temperature initial is equal to 298, and that's in Kelvin. We know that the mass of the water total is equal to 1 kilogram. And we know that the number of moles of the water in the vapor phase is 0.3, and that's in moles. Let me check real quick. Pressure, we got that. Final pressure, we got that. Temperature, moles of water total, mass, I mean, and moles of water in the vapor phase. We got that. All right. Oh, actually, R, a constant, right? 8.314. That's in joules per mole. All right. Now we have all our initials, our initial conditions and constants. Now, we need to make a function where we hold our equations, right? And it's going to take some values. Well, the two values it's going to take are the unknowns, right? And root's going to sift through all the numbers and find the exact number we need for the final parameters. So it's going to take V total and final temperature, right? And then we can unpack that from V, what it takes as an input. Now, what are the two equations, you might say? Well, if this function is going to be taking in random values of V volume, total volume, and final temperature, it's going to create a different total final pressure and a different number of moles in of water in the vapor phase, right? So we want to find difference. We want those to be equal to the desired finals, right? The 200,000 pascals and the 0.3 moles. So in order to gauge that difference initially, we want to subtract one from the other. And eventually, we want them to, when one is subtracted from the other, if they're the exact same, right? It would equal 0. That would mean that we have the right number because we have now the desired final parameters. So let's do that, right? You'll probably see what I mean here in a second. So the pressure test value that we're going to get from the random values for the volume total and its final temperature, we want it to equal, right, the pressure, total final pressure, right? And well, we want to move that over. So that's, oh, I meant to press minus P total final. And that's the first equation that we get. And the same thing applies for the number of moles of water in the vapor phase. So N test minus number of moles of water in the vapor phase. All right. So that's what we have so far. And Python is putting that yellow squiggly under it saying, well, you have this variable here, but you don't have anything, you don't have a path, right? What we were saying earlier. So let's create those paths for it. Starting with the moles from the test value. That's going to equal, well, pressure of the water in the final phase times the volume of the vapor phase final divided by R times the temperature final. Oh, oops, did not mean to do do that. And that's that right here. And let's do something for P tests as well. Pressure test values. Pressure test will equal pressure of the air final plus the pressure of the water final. And now, how do you find the pressure of the air final? Well, that was this equation earlier, right? Pressure air final equals moles of air times R times temperature final all over the volume of the vapor phase final. And now we need to solve for N air, because that's also an unknown. So N air, moles of air, uh, equals the pressure of the air initially times the volume of the vapor initially divided by R times the temperature initially. Now we have another problem where we need to set up the pressure of the air initially. And let's see that relationship again. Well, it's simply a rearrangement of this equation earlier. So P total, pressure total initial, minus the pressure of the water initially. Now, we have some paths that we have not created yet, as being the pressure and the volume, so let's do that. The pressure of the water initially will equal the Antoine equation. Well, we'll find the pressure here using this. This actually has a more sophisticated version of the Antoine equation and thus give a much more detailed, more accurate value. So we'll be using this, and it requires the temperature, and this is, since it's initial, we'll use temperature initial. And it's the same exact setup for the final pressure as well. So I'll simply just change that. And now we have the pressure of the water initially and final. So now we need to find the volumes. Well, how did we find the volumes? Well, we needed the liquids, volume of the liquid phases, initial and final, right? So volume of the vapor phase initially equals the volume of the total volume minus the volume of the liquid phase initially. And this is the same exact method that we'll find for the final. So now we need to find the volume of the liquid initially and the volume of the liquid final. So volume of the liquid initially, it was all liquid, right? So we can use M, mass of the water total, divided by the property of water, density of water. So roll temperature initial and volume to liquid final. There's vapor volume now, so we have to account for that. So mass of the water vapor, parentheses, divided by the property of water, density at the final temperature. And now we have one last connection that we have to make before they're all connected and we can solve it. And that is the mass of the water vapor. And that equals the number of moles in the water vapor phase times 18 times 10 to the negative 3. There we have it. We have created our pathway for the function root to find our values. So let's use root. Root needs our equation, right? So just EQS, and needs some test guess values. So let's just put in 350 and 0.1, and this is a good guess. So, and the solution converged, and we have our solution here. So I'll do .x here, so it only shows the solution, and here we have it. It is volume total here, and this is in cubic meters. So, and here we have it, and here's our temperature, and this is in Kelvin. And that's what we have. Thank you for watching.